Hello friends, this is lesson 21st part 2, and here we are going to talk about another type of machine learning which is called unsupervised machine learning. In unsupervised machine learning, in first part, if you remember, we talked about clustering, but here we are going to talk about dimensionality reduction, the second type. But before that, we are going to talk about curse of dimensionality, then we will talk about features extraction and feature selection, then we will give some examples for them. Now let's start with the first topic. So the first topic is curse of dimensionality. So what is curse of dimensionality? It is very important, friends, you have to understand this. So curse of dimensionality, it refers to the phenomena that occurs when classifying, organizing or analyzing high dimensional data. When we say high dimensional data, you should understand that the data or the data set has more number of columns. For example, hundreds of columns or thousands of columns. So that type of data there, whenever we are applying like any operation for classification or maybe organizing the data or analyzing the data, it is so much difficult because we have so many dimensions or number of columns or more there. So it is called high dimensional data that does not occur in low dimensional space. So specifically the issue of data sparsity. So data sparsity means, friends, when the number of dimensions are increasing, so here data sparsity happens there, because here as we are increasing the number of columns are increasing, so exponentially there the number of dimensions are also increasing. So for example, from 2-dimensional it will go to the 3rd dimensional, 4th dimensional, 5th dimensional. The number of dimensions are increasing like that. If the number of dimensions are increasing, then data sparsity happens there. The data will be so much spread out from each other, the data points. So the number of dimensions are more, and that is called curse of dimensionality. Friends, one thing you have to understand, by adding the features, the model what we are building will be okay, somehow the accuracy increases, the number of errors are decreasing, but it is up to certain limit. If it is crossing that limit, then it will act in reverse order. The accuracy is also reducing and the number of errors are increasing. So that point is called the threshold. It is not like simply just add the number of features, then you will be getting the high accuracy of your model, and number of errors will be less there, and the model which you build up, it is a strong model, or you can say it is a good model because it has highest performance and also less number of errors. Okay, somehow it is okay, but it has some limit. For example, if you are adding the number of features, then it has a limit until it reaches the limit. So it is right, the accuracy is increasing and also number of errors are decreasing, but after this limit it will act in reverse order. Again the accuracy will reduce, the number of errors are increasing because the data gets sparse. So that you have to understand this. So that is called curse of dimensionality. As the number of dimensions are increasing, so that will definitely affect the model performance. So now that is the reason we are going for dimensionality reduction. So what is dimensionality reduction? So in unsupervised machine learning, the second type is called dimensionality reduction. The name itself indicates that we are reducing the number of columns. If the number of columns are increased here, so the model performance will be not that much good. It will the accuracy will decrease and number of errors will increase. So many other problems will be there, especially sparsity of data. So that is the reason we are going to reduce the number of columns. So not the number of rows only, we are reducing the number of columns. So this process is called dimensionality reduction. So now we are going to talk about feature selection and feature extraction. These are the two topics under dimensionality reduction. So dimensionality reduction, we talked, we are reducing the number of columns. So here we have two types here, feature selection and we have feature extraction. Now let's see what is feature selection. So feature selection is, friends, it is getting a subset of columns or features only by using the best features. So if we have a set of features, just by taking the subset from that, so that subset is called feature selection. One thing you have to remember, from the existing ones, so we have already the columns or we have already the features. From these features we just take the subset, so that is called feature selection. Let me give you an example, then you will better understand. For example, if the model is predicting the salary of an employee, so we have these many features, but some of these features are not required for predicting the salary of employee. Like for example, we don't need the ID of the person, we don't need the name of the person, we don't need this sex of the person, date of birth of the person. So these are the features through which we can predict the salary of a person, like the qualification, the degree, whether master, PhD, or 12th standard, he is or she is bachelor or what. So then the seniority is required here, experience, then we go for discipline of the person. So these features, three features, we are taking from the first list, so this becomes the subset of the first list. So this type of reduction is called feature selection. So we are taking a subset from the existing ones. I hope you understood this. Now let's see what is feature extraction. So feature extraction, mathematically transforming our features or feature set into a new extracted coordinate system. It means we are extracting new features from old ones. Maybe the old ones are also there, but mostly we are extracting the new columns, which are called super columns, from the existing data. Here we cannot add or, for example, remove some columns. So just what we are doing, we are going to take some columns from this or a subset of columns here. But in feature extraction, the new features will be created by the model, and that is based on, for example, maybe a relationship, the strongest relationship, or we can say like the correlation between the variables. Based on that, the new columns will be created. Those columns are called super columns, and the process is called feature extraction. I hope you understood this. Now the model for doing this is called principal component analysis. For feature extraction, we will be using this this model, which is called principal component analysis for feature extraction. So I hope you understood these things. Now let's see practically how we can apply and see all those things. Now we talked about unsupervised learning, and then we said in unsupervised learning machine, there we don't have labels data, and then we are going to talk about the dimensionality reduction, which is a type of unsupervised learning machine. The first type was clustering. Now, so we talked about curse of dimensionality. It refers to the phenomena that occurs when classifying, organizing, or analyzing high dimensional data, means if the number of columns are more there. So this curse of dimensionality happens there. So that does not occur in low dimensionality space. If the number of dimensions are less, though, then curse of dimensionality does not happen there. But if we have more dimensionalities, so these problems will be there. Then what happens if we have this? Then that is called data sparsity will happen there. The data will be so much spread out from each other, the data points. Now data sparsity happens when moving, see friends here, when moving to higher dimensions, which create the following problems. For example, if simply we are adding the number of features, some people may think just by adding the number of features the model get better because accuracy is increasing and also the number of errors are reducing. So we also prefer a model which has the highest accuracy. Yeah, it is right, but it is up to certain limit. After the certain limit, if you are adding the new features, so it will act in reverse order. So again the complexity increases there, the space volume is increasing, data sparsity will be there, then accuracy reduces and number of errors are increasing. So it will act in reverse order. That you have to remember. Some certain limit, in that limit is called threshold. Let me show you this example, then you will better understand, friends. For example, if you are building a model and there we have only one feature, okay, from one feature you cannot, like, it is a model but it is not that much accurate model, because for example if you are predicting the salary of an employee based on a single feature, like maybe experience, working experience, is it enough for predicting the salary? You will see yes, but it is not like it is not efficient, because we should have more than few, at least few features should be there, then the model will be predicting the correct and accurate result. So if you are adding second features, we are adding two features and building the second model. Here we have two features, again this model is better than this model, but here again you added another feature, three features we have, and build another model, model 3. Yeah, model 3 is better than this and acting better than the first model. And again if you are adding the fourth feature and you will building another model called model 4, yeah, it is better than first, second and third. But if you are adding some new features again, so it means you are crossing the threshold, then the model will act in reverse order. Up to here the accuracy was increasing, the number of errors were less, so we built a model and that model was with the highest accuracy or performance accuracy. Then after that still you are adding the features, that is called curse of dimensionality. It means here after this threshold, curse of dimensionality, it means you have increased the number of features and working the model with highest number of features, so that problem will happen and it is called curse of dimensionality. So it will act in reverse order. These will be the problems here. Now see, one simple example is here, friends. So these are the features and we have the object here and the model is built like we have 4 features, but we want to predict the model, we want the model to predict the objects, and the object is we want the model to predict the ball, cricket ball for example, and we are going to give these features for predicting the cricket ball. So first feature is sphere. We check whether the ball is sphere or not. Yes, the ball is sphere. Let's see, the ball is eatable or not. No, the ball is not eatable. So this was yes, this is no. Whether we can play with that or not, yes, we can play with that. So this is also yes. Whether it is white or not, so we cannot say it is white, because the ball is not always white. It may be green, it may be red, or it may be some other color. So it is not always white. So this also, see, like these features, if these features are there, so these features are not that much strong features, it is affecting the model. So these are called the curse of dimensionality, which affects the performance of your model. Now if you are giving the orange, yeah, it is sphere, it is eatable, but we don't want eatable because we are predicting the model. So for orange it is no, because we don't want that. Orange is not, orange is eatable but it is not required for the model. Whether we can play with that, no. Is it white? So again the question is there, whether it is white or not. So for that, if we have increasing the number of features like this, so curse of dimensionality happens, and exponentially the number of dimensions are increasing. For example, here see this figure, the number of dimensionality representation. If we have, for example, 4 regions are there and we have only one dimension and all the data points are laid out on a single dimensional. Now if you are changing the dimensions, exponentially the dimensions are increasing. For example, we have 4 features or 4 regions here. Now it becomes 4 to the power of 2, so that becomes 16. So how many cells are there? 16 cells are there. And again if you are increasing that, so it becomes 4 to the power of 3, and that is nothing but 64, and like this it becomes third dimension, fourth dimension, a number of dimensions are increasing, and now you can see here all the data is close to each other. Here somehow it is sparsed, but here it is further sparsed. So the sparsity of data is more here because the number of dimensions are more, the sparsity of data is also more here. I hope you understood all those things. Now let's see, that is why we are going for dimensionality reduction. So dimensionality reduction, as we talked about, it is nothing but reducing the number of columns but not the number of rows. So there are two types of that. We have feature selection and feature extraction. In feature selection, if you remember, we are just taking a subset of the features from the existing ones. The features are already there, just we are taking a subset of that. I give you example here. I hope you understood this example. See, some people are confused with feature selection and feature extraction. You have to understand that. So just we are taking a subset of the existing ones. This you have to remember. But here, let's go and see feature extraction. So feature extraction is something that we are extracting new columns from the data, new coordinates, or we can say super columns from the data. If that is the process, so that is called feature extraction. And for that, we will be using the model called principal component analysis. So this principal component analysis is used to extract a set of numbers super columns in order to represent our original data with much fewer columns. We are just reducing the number of columns, but these number of columns which are reduced, and they are called super columns, and these columns are in such a position that they can represent the whole data for us. Just we are reducing the number of columns, and that is called the dimensions. Let us have the example of email. If you remember this data set, you are familiar with this. So I am reading the data set here and I am dropping the null values from that, and let me execute it here, then you will better understand. Yeah, so this is my data set. These are labels, ham or spam, and these are the messages here. Now friends, if you are feeding this to the model, what happens? You know that because we have two columns here, but actually this cannot be directly fed to the model, because the model needs quantitative values, so they should be converted to numbers. If now we are converting this to numbers, we have to apply tokenization there and then vectorization there. So if we are applying tokenization and vectorization, so for each and every word a separate column will be generated for each. And now you think how many columns will be there? How many columns will be there? Although we have how many rows? 5,572 rows we have in two columns, and now you think that for each and every word, if there is a separate column, so how many columns will be there? So more than 1,000 columns we will be having there. So many columns will be there. And the repeating ones, for example, if this is go, if we have another go, that go just the number is increased here, one column will be created for go, and just the number of that goes, how many this one word is repeated, that number will be written under this column. That you have to remember. That will not be repeated, just the same word will be once, but the numbers will be increased here. If you remember in tokenization and vectorization, there I showed you everything, so I hope you understood that. Otherwise you have to refer that lecture, then you will better understand. Now let's see here friends, I am creating a model here before applying the principal component analysis, and then we will see how many columns we are having, and at the same we will see the accuracy of the model for that. So for that I will be using logistic regression. So maybe you are using like decision tree, anyone you can use here. So from scikit-learn I need some like the metrics I want to calculate, then I want to call this function for splitting the data. In here, because we are dealing with text data, we have to vectorize that, we have to numberize the each and every word like that. So here I have splitted the data, we have two columns there, message was here, and then we have the labels. So they are splitted into x train, x test, y train and y test. Now I am instantiating the vectorizer because I have to change the text into numbers. Here I have converted the data which was in the form of text, and that is converted into document term matrix. So it is converted to document text matrix. So here again we are changing the test of that also. Here it is twin, and this one is test of that x twin, and here we have x test. And then I create the object of this model, logistic regression. If you remember, now I am fitting the data to the model, and now we are going to predict. Here we are predicting, and then I want to print the number of columns here. The shape, if you remember, that is showing us the number of rows and number of columns, how many rows and columns we have. So it is showing us here. So how many rows we have? Yeah, 1393. And how many columns are there? Although here, if you remember, we had only 2 columns, but after vectorizing the data or tokenizing the data for each and every word, it will create a separate column. So that is why the number of columns are increased to 7487. So these many number of columns we have, but the accuracy is good because it is already 98%, 99% accuracy is there, because the data is so much clean. It is classified into ham and spam correctly. And now let's apply the PCA. It means we are reducing the number of dimensions here. So for that, from scikit-learn, what I am doing, I will be importing this one, decomposition. We are decomposing the data now. Here see again the same steps. The data is split into training and testing. Vectorization is here. So here I will create here, instantiate the PCA object, and I say how many columns I want. So number of components, I say I want only 100 columns. From how much? From 7487 columns, I want to reduce it to how much? 100 columns. And then we will compare the accuracy, how the accuracy is increased or decreased, and then you will better understand that. So I am converting the data into the matrix, and I am okay, I am using this function to dense, because whenever, see friends, whenever we are converting this data to matrix, so what will happen? So we will be having so many zeros there. Why? Because the columns, the number of columns are increasing. So what about the number of rows? The number of rows will be filled with zeros, because for Go, if this is the first column or the second column, okay, three times it may be repeated, 4 times it may be repeated, okay, that we will be writing in second row. What about the third row, fourth row, fifth row of that column? So those values will be filled with zeros. This you have to remember, friends. So the number of zeros also will be so much there, because to fill all the rows. So what I am going to do here, yeah, I am converting it to dense matrix. Dense matrix means only the values, not the zeros. If you are not using this function, so it will consider the zeros also. So again I am converting it to dense matrix, so it will reduce the number of zeros or remove the number of zeros. It will consider only the words or the numbers what we have here, not the zeros. So here I transformed, here I used PCA and then transformed the data here, and now I created the model and I fit the data, and here I predicted, and see number of columns here, how many columns we have then. It's taking, okay. So see, still we have the number of rows, yeah, 1393 rows are there, but number of columns are 100. How many times it is reduced from this one? You count it. Here we have 7487 columns, but it is reduced to how many number of columns? It is reduced to 100 number of columns. So it is all done by the help of using PCA, principal component analysis, which is used, this model is used for reducing the number of columns or features extraction we are using for feature extraction. So I hope you understood that, the concept you understood. Now see friends, let's see the accuracy and compare the accuracy. The accuracy, see, here we have only 100 columns, and still the accuracy is 98%. So this model is better than the previous model because this model is faster. We don't have that much number of columns. Only with 100 number of columns, still we are getting the same accuracy, although this accuracy was achieved by using how many columns? These number of columns. Here this one is heavy, but this model is faster and it is less number of columns, 100 columns, and still we have the same accuracy, 98% we have. It is not like you have to always use 100 columns. You can change it like to 200 columns if you want, 300 columns you want. So it will convert all those number of columns. It will extract some few super columns among all those 7487 columns. It will choose only the super columns, new columns, based on some close relationship or correlationship in between. So it will select randomly those columns, and you see with the 100 columns still we are getting the same accuracy. But this model is so much faster compared to this model, because here the number of rows, okay, the number of rows are the same, but the number of columns, you see how many columns are there, 7000 columns are there. So here we have curse of dimensionality, we have here so many dimensions are there. The model okay, the model is the speed is reduced here. Okay, then let's talk about the feature extraction, its advantages. So what is the advantage? The first advantage, you see, our model or models become much faster. Then I hope you understood what I'm talking about, because here I'm using how many columns are there? Only 100, but still we are getting the same accuracy. But in the previous model, there we had 7487 columns are there, and that is called curse of dimensionality. So many dimensions are there, and that is definitely affecting the speed of your model. So that is why it is better to reduce the number of columns. Okay, our predictive performance can become better. Yeah, here it is better than that, because only with 100 columns we are getting the same accuracy. Because these 100 columns, you have to remember, these columns are nothing but super columns, the base columns among all those 7487 columns. Only base columns are selected. It can give us insight into the extracted features, so we can easily understand the internal pattern, how the data was like intercorrelated with each other by using feature extraction. Just by adding and removing the number of columns here, you just increase and you can understand how many columns. If we add, what accuracy we will be getting, 200 you put here, 300 you put here, then 400, 500. Then based on that you can easily understand the internal pattern between the data, how these features are related inside with each other. So the disadvantage, let's see the disadvantage. Yeah, the disadvantage is also there. We lose some of the interpretability of our features, as they are new mathematically derived columns. What we said, these 100 columns are nothing but the new feature extracted from those 7000 features. They are new, and that is why compared to the old ones, they are new. So we will be using how much columns we lost here. So many columns we lost, around 7387 columns we lost, and we got only 100 columns, and these 100 columns are nothing but the super columns. Yeah, the data loss will be there, but the model will be so much fast, and it will be still, if you are getting the same accuracy, so it is better. But if you are not getting the same accuracy or more than that, you have to change the number of columns by adding and reducing the number of columns. We can lose predictive performance because we are losing information. Yeah, it will definitely affect the performance also, because whenever you are losing the information, it affects the performance also. Here, if you remember, somehow it is reduced, not that much, but still, if you are rounding this number, so it becomes 99%, because it is 7 there. Here we have 7, the third value, 7. But here you see if you round this, still you will be getting 98%. So it is because so many columns we lost, but the model is so much fast. So I hope you understood, friends, about the second type of unsupervised machine learning, which is called dimensionality reduction. Then we talked about curse of dimensionality, and I gave you some examples here. I hope you understood these examples. And then we talked about feature selection, feature extraction, and the model which is used for extracting the features, that is called PCA. And then we give you some examples from whether this one data set, you're familiar with this emails, whether it is ham or spam. And then we applied the PCA here. Before PCA we calculated the accuracy, and after the PCA we calculated the accuracy, and then we reduced the number of columns to 100, and still we got the same accuracy with only few numbers less. And we talked the advantages and disadvantages of feature extraction. So here I give you the example of feature selection. This you have to understand whenever you are comparing feature selection and feature extraction. In feature selection, we are only taking a subset of the existing ones, but in feature extractions, we will be extracting the new features from old ones. These are called super columns. They may be the same column or maybe some other new generated columns. So it is based on the relationship between the columns and also based on correlationship between the columns. The model, since it is unsupervised model, so the model itself decides which columns are more accurate and more related, so it will be clustering and grouping those columns. So based on that, the model will be built. So I hope you understood all these things, friends.